Sometimes we'll write programs that are all about raw functionality. But very often, we'll be writing programs who are going to be used by ourselves or other users who would like interacting with them to be a streamlined procedure. NetBeans, for example, is a powerful program that offers us a lot of functionality. And we access this functionality through a graphical user interface, these menus and buttons provided by NetBeans. In theory, NetBeans could have chosen to operate as simply a command line program. But in order to use NetBeans like that, we would have to memorize or look up a large library of specific commands for every action we wanted to take. A powerful and well-written application has a streamlined interface that guides us towards the important functionality and makes it easy for us to access. The Java Development Kit contains within it a Java extension library, the Swing library, which makes it very easy for us to wrap our own code in graphical user interfaces like NetBeans has. To start us off on this track today, we're simply going to write a program that will open up a new GUI window. At the heart of these Swing Java GUIs is the JFrame class. This will be, in our case right here, the actual window object that our operating system will handle and that we could move around our screen. And we can create a new JFrame just like we might create any other object. If we'd like, we can even pass some parameters to this JFrame's creation. If we just give it a string parameter, we'll be telling the JFrame what to present as its name. Once we've declared a JFrame, though, it's simply going to exist in Java's memory like any other object. It won't present itself to the user until we explicitly tell it to. This is simply a function call, though, to the setVisible function, and where we assign that value to true. Pretty easy, right? There's one more thing we should do before we make a JFrame visible, and that's to call this pack method. When we create more complicated frames, they may contain a lot of information, and in a GUI, much of this information takes up visible space. The pack method basically pre-builds the physical relationships between the objects in our frame and ensures that it doesn't behave oddly when it actually appears visible to the user. So this is a really simple program we've written so far. Only 3 lines of code and no real thought required on our part. When we run this program, it might at first appear that nothing has happened, but in fact, something has. In the top left-hand corner of my screen, a new window has appeared. And if I click on the right parts of this window, I can, in theory, drag it around, or we can just resize the window. This is a fully fledged window that our operating system can now handle us moving around, and it even supports dynamic resizing. You'll see that our header, which I've spelled wrong there, has also been appended to our window. There we go. That's fixed. So that's super basic. Let's see what else we can do with our existing JFrame. When our JFrame appeared, it was very small and hard to see. A program window of that minimum size is really never going to be useful to anyone. So let's see what powers frame gives us in terms of setting the window's size. We're very often going to use the setPreferredSize method to apply a size to our JFrame. There is also a setSize method But this method sometimes isn't going to give us exactly what we expect it to. Because our JFrame right now is set to be resizable, it's not appropriate for us to explicitly assign a size to it. Rather, we should instruct it that given no other input from the user, meaning resizing of the JFrame, the JFrame should be a certain size. We can store, manipulate, and create size information using the dimension class. To construct a new dimension, we can simply give a width and a height. So let's set our JFrame's preferred size, the size it would like to be until we stretch it at all, to be 400 by 400. Dimension lives in another library, so we'll have to import that library. And then we should be able to build and compile our project, and once again, open up our new GUI. So now we get a nice square GUI to start with. However, it's still pretty useless. There's nothing contained within this GUI. So before we end here, let's take a quick look at what it looks like from a programming standpoint to add elements to our GUI. Quite possibly the simplest element that we could put inside a JFrame is a JLabel. Labels are responsible for containing text. And instantiating them is extremely simple. We simply tell them what text they should contain. Of course, in more complicated programs and GUIs, this text can become dynamic and changing. But for now, let's just get some text to display. Simply declaring that we have a JLabel is not enough. We have not yet associated this label object in any way with our existing frame. Our frame, as you could probably tell by the vast array of methods and members it exposes, has a whole lot of components. And we need to know in which of these components to place our new JLabel. One of the components within our JFrame is the content pane. That's the area that we visibly see inside that window where things normally go in a program's GUI. So that seems like a reasonable place for us to add a new component. In this case, our label. Let's once again build our program, kill the old instance, and run our program. There we go. Now we have text in our GUI. We've successfully added an element to the content of our JFrame window. One thing that's kind of annoying is that our program has been continuing to run even after we close the associated GUI. That's a little silly. When I press this X on the NetBeans GUI, NetBeans closes itself and stops running as a process on my system. We can instruct our frame to terminate the associated process by using its set default close operation method. This method has return type void and takes an integer as a value. This integer is an enumerator, and there's lots of options available to us. All of these options are statically declared by the JFrame class. And the one we're probably looking for here is exit on close, which will exit our application when we close our window. Build, run, terminate, and there goes our process, not quietly running in the background anymore. That's our super basic introduction to GUIs in Java. Creating a GUI is complicated, exciting because it's visual and immediate, and also really powerful. One of the things that defines truly amazing software programs is their GUI and their user experience. Before we write this introduction off as done though, I'd like to show you something that's a bit heavy on the technical side, but is probably really good to see here. As our program stands right now, it's functional, but were we to extend it, we might eventually run into some very odd and very confusing issues. What we've done now flies in the face of the recommended practices when creating a new GUI. These recommended practices are in place to protect us from some very low-level issues that can occur when our programs become multi-threaded. What does that mean that our program is multi-threaded? Well, when we create our GUI, when we cause it to come into being, our program goes from performing a single task, simply executing the main method from start to finish, to performing multiple tasks, because now, in addition to executing this code here, it's also managing that new window we've created and any functionality performed by that window. To protect ourselves from the complexities of multi-threaded code, it's recommended that we create our new Swing GUI by allowing one of the Swing utilities to construct this GUI for us asynchronously. In order to make this happen, we're actually going to need to pull all the code we've written out of our main method and place it in one place where we can reference it from our main method, a new function. And we can just paste all of this code back in to our new function. Now, let's take a look at how Swing recommends we cause our GUI to come into being. As I said, Swing, the Swing package, provides us some functionality that will perform the vast amount of this work and thinking for us. The Swing Utilities class has a static invoke later method that will create our GUI when no other threads really need to be processing right now, or when all of the other thinking is done for a bit. This invoke later method expects us to pass a runnable object to it. So we're going to have to create for ourselves one of those. Runnable objects are those that can be converted into a thread of their own. They have a method that we're going to override that's called run. And the Swing Utilities invoke later method will call our runnables run method when appropriate. When that occurs, all we want it to do is to call our make GUI method and begin executing that code that we've just tested out will create a GUI. Oh, and we'll add our override notation to be good Java programmers and pass our new runnable object to the Swing Utilities invoke later method. And we've forgotten a semicolon somewhere. I've forgotten a semicolon somewhere. There we go. Run. Now, the functionality is exactly the same. And what we've done could be arguably overkill for a program this small. But it's really good for us to take a look at what we should expect to see in a larger software project, where things like multi-threading could become a concern. We went through this a bit quick, so let's stop and take a look right here. What we've done in this bit of code is created an anonymous class. While it looks like we've created a new runnable object, we've really created a new subclass of the runnable object with its own special overridden version of the run method, and just put that right in the middle of our code. This is a powerful methodology that allows us to cut down on the amount of code needed. Of course, if we overuse it, our code can quickly become very complicated for us or another programmer to read and understand. Thanks for watching.